An aircraft's main battery is made up of a number of secondary cells joined together in series to produce the required voltage. There are two types of secondary cell battery in common use. They are the lead-acid and the alkaline types. We will first look at the two types of battery, beginning with the lead-acid type. We will then look at how the condition of the battery is checked and maintained. One of the most common types of secondary cell battery is the lead-acid battery. The on-load voltage, or the voltage with the load being taken, of each cell of a fully charged lead-acid battery is 2 volts. The on-load voltage is also known as the nominal voltage. The off-load voltage, or voltage with no load applied, is 2.2 volts. A 12-volt lead-acid battery consists of 6 cells connected in series, and a 24-volt battery of 12. The active material of the positive electrode, or plate, is lead peroxide, and that of the negative plate is spongy lead. Both plates are immersed in an electrolyte solution of water and sulfuric acid. The liquid level should be just above the top of the plates. The container is glass, or more usually hard plastic, with a filler cap to allow topping up with distilled water to replace water which is lost through evaporation during use. A vent hole in the cap allows the escape of hydrogen gas, which is produced when the cell is working. The state of charge of a lead-acid cell can be determined by measuring the strength of the electrolyte solution. This is done with a hydrometer, which measures the specific gravity. The specific gravity of a liquid is defined as its weight divided by the weight of an equal volume of water. A fully charged cell will have a specific gravity of 1.27. When the cell is connected to an external circuit and current is flowing, the acid becomes weaker, and its specific gravity falls. The voltage also slowly reduces. When the specific gravity has fallen to 1.17 and the voltage to 1.8 volts, the cell should be recharged. To charge a cell, it is connected to a battery charger, which applies a slightly higher voltage to the cell and causes current to flow in the reverse direction through the cell. The current flow causes the chemical constitution of the electrolyte to change, producing an increase in its specific gravity back to 1.27. When charging a lead-acid battery, it is important that the rate of charge is controlled. Charging too quickly can cause gassing and evaporation to occur, which may lead to a total loss of the acid, causing damage to the plates. The performance of a lead-acid battery is affected by its temperature. With a low battery temperature, the rate at which the battery can be discharged is decreased because of higher internal resistance. In general, the battery performs better when it is kept warm. As we have already said, when a lead-acid battery discharges, the specific gravity of the electrolyte reduces. This increases the temperature at which the electrolyte will freeze. In very cold temperatures with a discharged battery, there is a risk of the electrolyte freezing and damaging the battery. It is therefore important to maintain the battery in a fully charged state during winter operations. Electrolytes are highly corrosive, and if spilled in aircraft, can cause extensive damage. The neutralizing agent to be used on an acid electrolyte spillage is a sodium bicarbonate solution. In older types of lead-acid battery, the acid is in liquid form, and great care has to be taken to avoid any spillage. More modern batteries are of the absorbed liquid type, where most of the electrolyte is absorbed into the active materials in the plates, making it less prone to spillage. Lead-acid batteries are still used in some smaller aircraft, but have been largely replaced by alkaline batteries of the nickel-cadmium or NiCad type. The plates of these batteries are composed of nickel oxide and cadmium, and the electrolyte is potassium hydroxide. The specific gravity of the electrolyte is in the range of 1.24 to 1.30. Again, the electrolyte can be highly corrosive. The neutralizing agent to be used in case of a spillage is boric acid. However, the cells are all enclosed in a sealed metal container, so the risk of a spillage is very small. The on-load voltage of one cell is approximately 1.2 volts. A 24-volt battery will consist of 20 cells in series and a 12-volt battery of 10. Unlike the lead-acid battery, the voltage variation from fully charged to fully discharged is very slight. Here is a graphical representation of a comparison of a lead-acid battery against that of a NiCad battery during discharge. As you can see, the NiCad battery holds a much more constant voltage during the discharge cycle. Unlike the lead-acid battery, the specific gravity of the nickel-cadmium battery electrolyte does not change, and as we have seen, the voltage variation from fully charged to fully discharged is very slight. The only way to determine the state of charge is to carry out a measured discharge test or capacity test. Nickel-cadmium batteries are not affected by low environmental temperatures in the way that lead-acid batteries are. And because the specific gravity of the electrolyte remains high, there is no danger of it freezing. A NiCad battery has a low internal resistance. Because of this, it is capable of supplying very high currents during its discharge cycle. This type of battery is often used to drive the starter motor of an airliner's auxiliary power unit. The nickel-cadmium battery normally has a metal case, unlike the hard plastic of the lead-acid battery, so it is more robust. It is also more compact than a lead-acid battery of the same capacity. NiCad batteries can have a problem with the amount of heat generated during charging. In certain conditions, heat is generated faster than it can dissipate, so causing a rapid increase in temperature. This has the effect of lowering the effective internal resistance of the cells, thus allowing an ever-increasing charging current and subsequent increase in temperature, which, unless checked, leads to the total destruction of the battery. This condition is known as a thermal runaway and can cause so much heat that the battery may explode. For this reason, the charging of a NiCad battery must be closely monitored. A built-in thermal switch monitors the battery temperature and operates at a preset temperature, isolating the battery from the charging source until the temperature reduces back to an acceptable level. There may be an indicator light on the flight deck to alert the pilot when the temperature switch operates. As we have already said, the capacity of a battery is the product of the load in amperes that the manufacturers state it will deliver, and the time in hours that the battery is capable of supplying that load. The capacity is measured in ampere hours. Actual capacity is determined by the battery's deterioration in service. If a 60 ampere hour battery, when subjected to a 60 ampere load, lasts only 42 minutes, then the actual capacity is 42/60ths, or 70% of its rated capacity. In other words, the battery is only 70% efficient. A capacity test, which is a test to determine the actual capacity of an aircraft battery, is carried out every 3 months, and the efficiency must be 80% or more for the battery to remain in service. This capacity will ensure that essential electrical loads can be supplied for the time stipulated in EASA regulations, following a total generator failure. Essential loads will include aircraft attitude information, essential communication equipment, standby lighting, pitot heat, plus any other services necessary for continued safe flight. Spare batteries will be held ready for use in the electrical workshop. Lead-acid batteries are stored in a charge state to prevent deterioration of their plates. NiCad batteries can be stored in a discharge state with no detrimental effect to the battery, and therefore have a longer storage life or shelf life. The pilot's pre-flight check of a battery may include comparing the on-load voltage with the off-load voltage to give an indication of the state of charge of the battery. If the battery is not supplying any load, then it will show its off-load voltage. If the battery is then loaded up by switching on selected loads and the voltage is maintained, then the battery is in a good state of charge. If the voltage falls below a stated value within a time limit determined by the manual, then the battery is in a low state of charge and should be replaced. As we know, a battery is made up of a number of cells in series. If any single cell should fail, the battery voltage will probably fall to 0. The battery will be unserviceable and must be replaced. A constant voltage charging system using the engine-driven generator is employed with most lead-acid batteries to maintain the battery in a fully charged condition during flight. With this system, the output voltage of the generator is maintained constant, at 14 volts for a 12-volt battery and at 28 volts for a 24-volt battery. With Nickel-Cadmium batteries, which are susceptible to thermal runaway, a dedicated battery charger which monitors battery temperature and voltage is used. Some Nickel-Cadmium battery charging systems use a method known as pulse charging. In this type of system, the battery charger delivers short pulses of charging current. After starting an engine using the aircraft's battery, the generator, when it is online, recharges that battery. This is indicated by the high initial reading on the generator's ammeter or the center zero battery ammeter. This reading should quickly reduce as the battery is recharged. But if the charge rate increases or remains high, it could be an indication of a faulty battery. A continuing high charge rate could result in a battery overheating and subsequent damage. That is the end of the lesson. On screen is a summary of the advantages that Nickel-Cadmium batteries have over lead-acid batteries. The main disadvantage that Nickel-Cadmium batteries have is the more complex charging procedure required to avoid thermal runaway. Spend a moment studying this table, then move on when you are ready. Displayed on the screen is a summary of the two types of battery. Again, spend a moment studying this before moving on. Here are the other important points that you should take from the lesson. A battery capacity test is carried out every 3 months. A battery must display an efficiency of 80% or more to remain in service. The flight deck battery check is carried out on load, which is with a load applied. If one cell fails, the battery is unserviceable and must be replaced.